Hello, this is tutorial number 4 of power systems, and in this tutorial what I'm going to address is transmission lines. So you have covered some part in the lecture, so therefore I'll show you here how to calculate some properties of transmission lines using the equations that you have learned in your lecture. So first of all, we'll identify what are the transmission line components. So there are many components in transmission lines. Okay, so uh, as you know, the main component is actually the conductor. But other than that, there are many other components in transmission lines. That means associated with transmission lines, there are many other components. So as an example, if you take a tower, right, uh, in order to connect transmission line, we need a tower. So therefore that is also a component that we need in transmission lines. Okay, and there are some other types called insulators, right? So insulators means in order to prevent that high voltage touching with the ground or with the towers, we have to use insulators. So you will learn about those things in your lectures, but I will address you the conductors and how to find their properties. So first of all, I will introduce there are actually two types of conductors. So one is the homogeneous, the other one is the non-homogeneous. So homogeneous ones, there are all aluminum conductor AAC, then triple AC all aluminum alloy conductor. In a non-homogeneous, there will be ACSR, which is the most common type, aluminum conductor steel reinforced. Then ACAR, aluminum conductor alloy reinforced. ACSR, aluminum alloy conductor steel reinforced. So most of the time what we are going to use is aluminum conductor steel reinforced. So what we are talking about in here is this steel reinforced and everything, they are actually addressing how the core of a conductor is made. So as an example, if we just have an aluminum conductor, the strength of that aluminum conductor will be very much less, because aluminum is not a good uh, um, not good in high tensions. But if you take steel is in it is very good in high tensions. That means it can hold some tension, and actually what it can do is it can hold the conductor also. Conductor means the current carrying one. It can be it can hold it. So as an example, let's say you are laying overhead transmission line, which we are calling as OTL. So at that time, um, between two towers, the conductor or the current carrying thing, it carries some weight. So that weight will be applicable to the transmission line. If we cannot withstand with that weight, if the transmission line cannot withstand that weight, it will collapse. So therefore there should be some arrangement in order to hold the transmission line. So therefore there will be steel strands, that means steel core inside of the mm, inside of the conductor. So so as an example, in ACSR, aluminum conductor steel reinforced. So using that steel reinforcement, what we can do is it can withstand high tensions. Okay, as I have told you previously, ACSR is the most common conductor type, right? Which consists of layers of aluminum strands surrounding a central core of steel strands. Okay, so which give the conductor high strength to weight ratio. High strength to weight ratio means strength is how much tension it can handle, and weight means the total weight of the transmission line. Okay, so the strength should be able to handle the weight, so otherwise the transmission lines will collapse. So another thing is, as I have told you, we are talking about OTL conductors, which is overhead transmission lines. So when there are overhead transmission line in ACSR case, what we don't have is an insulating cover. So there will be insulators in order to hold this conductor, but there won't be insulating cover around the conductor. So therefore, that's because the people cannot reach to that level. Most of the time they cannot reach. So even though they reach to that level, what should happen is, in order to electrocute it, there should be at least two conductors or two phases should be touched. So that thing will not happen, right? So as an example, so if there's some kind of bird or an animal or small animal uh, walk on these conductors, they won't get electrocuted. They won't get electrocuted. They won't get until they hit with two until they touch with two conductors. That can be between two phases, right? So therefore, this OTL conductor ACSR, most of the time they don't have insulating cover, right? And also they will carry high voltage. Okay, they will carry high voltage, and therefore, in order to form, right? In order to form, or in order to carry one phase, right? Okay, so most of the time, so there will be more than one conductor per phase forming a bundle of conductors. Okay, so you can understand that. That means there won't be any single conductor, right? Because because if we have a single conductor, what will happen is actually the resistance will also increase. But if we use few conductors, right, like two conductors, as you can see in the figure, three conductors or four conductors, it can reduce that resistance also, right? So therefore we will call these things as bundle of conductors. Okay, so most of the time they are in like 2, 3, 4, likewise. So you can see it in here. So that simple d, that will represent the distance between those um, lines, right? Those lines. So as an example, let's say that second one, which has three conductors. So that three conductors, they will have the same phase. Okay, but they are using three wires or three conductors. You can see that in here. Okay, so then we'll move on to the most important parameter of uh, the transmission line, that is the inductance. Okay, that is the inductance. So when we are calculating inductance and any other properties in transmission lines, since they are since there's the length factor, right? Length means so we are not actually representing the parameters like just let's say inductance. It is not in Henry, it will be in Henry's per meter. Let's say if you have a capacitance will be farads per meter, resistance will be ohms per meter. So likewise we will have the per meter. So we are calculating these parameters for 1 meter, right? So that's why you can see it in here. Our um, units are Henry per meter. Okay, so lx so we'll consider conductor x, right? In that conductor x, the inductance is Lx. Okay, so it will represent like Lx, and Lx is equal to lambda x over I. Okay, so if you can recall what is actually lambda? Lambda means what? So if you can remember, Li is equal to phi. Phi means actually that is the flux linkage. Okay, so therefore lambda x means flux linkage of conductor X, right? Then I means the current. Okay, so inductance is calculated like flux linkage per ampere is called the inductance. Okay, so then uh, we, we are not going to derive this thing, we are not going to derive this equation, but it has found that uh, Lx, that is equal to 2 into 10 to the power minus 7. Ln means uh, log base e. Okay, gmd divided by gmr. So what is meant by this gmd? Okay, so when we have conductors, right? So there are basically two things that you are going to refer, right? So GMD means geometric mean distance. GMD means geometric mean distance. Okay, so in this one, this is GMD of conductor X, right? GMD means geometric mean distance of conductor X, right? Then GMR means geometric mean radius. Okay, so geometric mean radius, that is called GMR. Okay, so most of the time this GMD and GMR we are referring as dxy over dxx, right? So actually this equation below, Lx equal to 2 into 10 to the power minus 7 ln dxy over dxx Henry per meter, it is written for when we have like two types of conductors. So I'll give you that example also, right? So what you have to understand is the answer will be in Henry per meter. We'll see this example. In here we will have two conductors. One will be conductor X, the other one will be conductor Y, right? And conductor X will have 1, 2, 3 lines. They are named as 1, 2 and 3. Then we will have conductor Y. So in there it is named as 1 dash and 2 dash. Okay, so 1, 2, 3 they are belong to conductor X, so that is why it is n is equal to 3. Conductor Y 1 dash and 2 dash, it is belong to m equal 2. So for each line we have in here, this Rx or the radius, that is equal to 0.03 meters. Okay, so for Ry it is radius is equal to 0.04 meters. So let's say between 1 and 2 the distance is 0.5. So we can represent that distance like d12 equals 0.5. d12 means, d means distance between 1 and 2, 0.5 meters. So distance between like 2 and 3, it is d23, it is equal to 1.5 meters. So let's say the distance between 1 and 3, that is equal to 0.5 plus 1.5, that is equal to 2 meters. So likewise we can represent the distances between these things. Okay, so I will show you how can we calculate the inductance of these. So the GMD. Okay, so can you remember what is GMD? GMD is geometric mean distance, right? When we have to calculate the geometric mean distance, right? So when we have two conductors, we have conductor X and Y, there will be only one GMD. Okay, so we are representing that GMD as dxy. Okay, dxy. Okay, and that is equal to, right? So consider in the conductor X we will have three lines, right? And conductor Y we will have two lines. So D11 dash, right? D11 dash, that will represent the length or distance between line 1 and 1 dash. Okay, then multiply D12 dash. D12 dash means distance between 1 and 2 dash. Okay, so then can you see the pattern? Then we are writing like D21 dash. D21 dash means distance between uh, line 2 and line 1 dash. Okay, multiply D22 dash, the distance between 2 and 2 dash, multiply D31 dash, distance between 3 and 1 dash, D32 dash, distance between 3 and 2 dash. Okay, so you can see 1 D11 dash, D12 dash, D21 dash, D22 dash, D31 dash, D32 dash, right? So we have to altogether there are 6 things, so we have to multiply everything together, then we will have to find the uh, 1 over 6th value, that means 6th root, right? 6th root of this thing. So that means, so it is like you have to get the 1/6 of this multiplication or 6th root. So likewise, okay, then you can find what is dxy. Okay, then GMR. So what is meant by GMR? GMR is geometric mean radius. So geometric mean radius is calculated for two conductors, right? That means we are calculating for conductor X at one time, then conductor Y another. Okay, because there are two conductors, so for two conductors there will be like two inductance values, right? So in order to find the total inductance, we are going to add these two, right? So that's why GMD is common and GMR is particular for that conductor. Okay, so this one, what is dxx, right? D, if you refer this one, dxx is equal to d11, right? So it says d11 according to our 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 definition. D11 means distance between line 1 and 1, right? So it is like, it doesn't make any sense, right? But we'll, for the notation we will write it down, right? But then I will explain how we can calculate D11 and what is D11. Okay, then D12, what is D12? D12 is the distance between line 1 and 2. Okay, then what is D13? D13, that is the distance between 1 and 3. Okay, so can you see that in here we are considering only conductor X, right? Here we are considering only conductor X. Then D21, distance between conductor 2 and 1, which is same as D12. Okay, so what is D22? Again it will not make sense because that means distance between 2 and 2. Okay, then D23 means distance between 2 and 3. Okay, D31, distance between third one and first one, which is equal to D13. Then D32, right? So this should be changed as D32. D32, distance between third one and second one, which is equal to D23. Okay, then D33 again same as D11, D22. Here we have D33. So I'll tell you how to find that D33 also, right? So then take the ninth root of that one. Ninth root, that means multiply everything together, then take 1 over 9th index, right? So then you are getting dxx, right? So here we are getting this thing because since we have 3 conductors, here we have 3 conductors, so we will have 9 things to multiply. Okay, then GMR of conductor Y is given as dyy. So what is d1 dash 1 dash? that is again, so now we are considering only conductor pi, right? D1 1 dash means distance between one dash line and one dash line. So again it will not make sense, but I will tell you again. Then D1 dash 2 dash, distance between 1 dash and 2 dash. Then D2 dash 1 dash, distance between 2 dash and 1 dash, which is equal to D1 dash 2 dash. Then D2 dash 2 dash, again the same thing, right? So here we will have four things. So therefore we have to take the 1/4 index of these things, right? So here we will have only two conductors, therefore we will have only 1 2 3 4 terms, right? So now we know what are the equations that we are going to use. Now we are going to find those values, right? So first of all we are going to find GMD, which is dxy, right? So what is d1 1 dash? D1 1 dash, distance between 1 and 1 dash, it is 0.5 plus 1.5 plus 2, which is equal to 4 meters, right? 4m, right? Then d1 2 dash, d1 2 dash means distance between 1 and 2 dash, so add 0.3 to 4, so 4.3. Then d2 1 dash, it is 3.5, because 2 1 dash is between 2 and 1 dash, so 1.5 plus 2, it is equal to 3.5. Okay, then d2 2 dash, okay, between 2 and 2 dash, it is 1.5 plus 2 plus 0.3, 3.8. Then d3 1 dash, d3 1 dash is distance from between 3 and 1 dash, so 2 plus 2, it is just 2, right? Then 3 2 dash is 2 plus 0.3, 2.3. Then when you substitute it to dxy, you will get 3.189. Okay, so as you can see, you will get 3.189. Now we have to calculate GMR of x, right? GMR of x. So as I have told you when I am explaining the previous slide, right? So d before looking at D11, D22 and D33, we'll take a look at D21 and D12, right? So D2 and D12 means distance between 2 and 1, distance between 1 and 2, which is the same thing, right? Then D23 and D32, which is the same thing, distance between 3 and 2 is equal to distance between 2 and 3, which is 1.5. Okay, then D31, distance between 3 and 1, then D13 is distance between 1 and 3, which is 2. Okay, so here D11 means, as I have told you, D11 and D22, D33, according to our notation, it is like distance between 1 and 1, distance between 2 and 2, distance between 3 and 3. It doesn't make sense, right? But actually what is in here is, it is a value that is given by this equation. So D11, D22, D33, that means if you have like D distance between the same line like this, D11, D22, D33, it is calculated like Rx multiplied by e to the power minus 1 over 4, right? So this thing is associated with how the flux will affect and everything. So in here I'm not going to explain that one, we will just use what is this, right? So for this one, Rx is 0.3, right? E to the power minus 1 over 4 is 0.7788. Okay, so when you have like D11, D22, D33, right, that means this distance between same line, that will be the radius multiplied by e to the power minus 1 over 4, right? E to the power minus 1 over 4 is a given constant, so that is a constant, right? So according to that, when we calculate it in here, it is equal to D11, D22, D33. They all have same Rx, because they all are conductors of lines of same conductor, which is conductor X, right? Then they will have same radius, right? According to our given example, Rx is 0.03, means for conductor x, radius is 0.03. So 1, 2 and 3, they will have that same radius. So therefore they will be 0.02336, right? Then if we substitute all these values to the previous dxs, which is the GMR of conductor x, what you are getting is 0.318 after you obtaining the 1/9 index of that. Okay, that means ninth root 0.3128. Okay, like we can do it for the conductor y also, right? In here d11 dash d2 dash 2 dash, that is same as the previous one, but here, right, ry means the radius of conductor y, that is different than the value that of x, so which is equal to 0.04. But again d1 dash 1 dash d2 dash 2 dash, that is equal to radius multiplied by e to the power minus 1 over 4. So as I have told you, this e to the power minus 1 over 4, that is a given constant. Okay, that is a given constant. So that is constant. Even though it is conductor x, y, z or anything, that value will be same, e to the power minus 1 over 4, which is equal to 0.7788. Then ry is 0.04, which is equal to 0.03115. Okay, then d1 dash 2 dash, which is same as d2 dash 1 dash, because d means that is distance between 1 dash and 2 dash, that is equal to distance between 2 dash 1 dash. What is that? It is given here, it is 0.3. Okay, so likewise substitute everything to the previous equation. Okay, dyy, so we are finding GMR of conductor y. Okay, so in this one we can find it 0.0315 multiplied by 0.3 multiplied by 0.3 multiplied by 0.03115, right? So if you take the 1/4 index of this or the 4th root of this one, you will get 0.09667. Okay, so now we have found GMR of conductor y. So likewise, what we have found, I will recall, right? We have first found GMD, right, which is common, or we are finding only one value when we have this setup, right? GMD, we will have only one value, right? Then, but we have to find GMR for both x and y separately. So we have found GMR for x, which is dxx. Then we have found GMR for y conductor y, d y y. So now we have all those values together, right? Now we are going to substitute it to the first equation. Okay, so like this, Lx means the inductance of the first conductor, right? Conductor x. So 2 to the power 2 into 1 2 into 10 to the power minus 7 into ln 3.189, right? So that is the GMD. Okay, divided by 0.3128, which is GMR of conductor x, and finally what you are getting is 4.644 into 10 to the power minus 7 henries per meter. So this is actually 0.4644 microhenries per meter. Okay, then Ly is the inductance of conductor y, 2 into 10 to the power minus 7 ln 3.189 divided by 0.09667. Okay, so this is equal to 6.992 into 10 to the power minus 7 henries per meter. Okay, so 3.189, that is the GMT, right? 0.09667, that is the GMR of conductor Y. Okay, so GMR is for the conductor, GMD is common. Okay, so as we have found these two values, so if you were asked to find the total inductance, what you have to do is you have to add these two values. uh, Total inductance L, that is equal to Lx plus Ly, right? Even though we are referring this as L, actually this is the units of L and Lx and Ly, they are henries per meter, right? But in this section we'll consider them as L, right? Because everything will be in per meter, right? So 1.164 into 10 to the power minus 6. When we add these two, 4.644 into 10 to the power minus 7, then 6.992 into 10 to the power minus 7, we are getting this 1.164 micro Henry per meter, as you can see it in here. Okay, so therefore now what we have, I will recall, right, what we have done. First we have identified what is Lx and Ly. So Lx is equal to 2.10 to the power minus 7 into ln GMD over GMR of x. Ly is equal to 2 into 10 to the power minus 7 ln GMD over GMR of y. Then we have found GMD, which is a common value. Then we have found GMR. Okay, for GMR when we are finding GMR, we have to find it for both conductors, conductor X and conductor Y. So what we have found is we have found Lx and Ly, right? Then in order to find the total inductance of this single phase line, we have to add Lx and Ly, okay, which is equal to 1.164 microhenries per meter. Okay, so what you have to understand here is I have shown you here how to calculate GMD and GMR. Okay, so we have manually calculated GMD and GMR values for X and Y conductors by using the given um, equations, right? So therefore we have done everything manually, right? This proof of this Lx and Ly, actually we can do it later, right? Okay, so we have calculated everything manually, but what you have to understand is there are some standard conductors, right? So it is not like we can calculate GMR and GM values by ourselves always, right? There are GMR and GMD values calculated for standard conductors, right? So there are standard conductors, right? So in the standard conductors, the manufacturer or the conductor manufacturer, they will provide you what is GMR and what is GMD of that particular conductor. So therefore when we were given GMR and GMD, we are not going to calculate those things. We will just substitute those values to that inductor equation. Then let's say if you were given GMR value of X and Y and the GMD value, right? So then what you have to do is you have to just substitute it to that previous equation in order to find the inductance. So likewise, we can calculate the inductance per meter. Okay, so uh, in here I have shown you just a particular arrangement, right? But when we are going into practical, right, this will not be the arrangement, it will be different arrangement. But what we have to do is we have to just substitute those equations. If you were not given GMR GMD, first you have to find out GMD, then you have to find GMR of the conductors, then you have to substitute it to the equations that was given to you, right? So what you have to do is next, um, take the question, right, then try to calculate it by yourself until you are getting the final inductance